Hello everybody. Today we have a very standard problem, and this problem is very critical to understand because almost all the other continuous charge problems follows the same pattern. Okay, so what we have is there is a point charge here. We want to know force on this charge. And then there is a continuous charges here, meaning of course they're made of maybe protons or electron, whatever, but it is continuous. It's you might say it's just a model of something that's the discrete nature is not important. There are way too many charges, and we can't really take account of them, so we can just say, hey, this much charge on average is distributed. One way to create something like that with a charge over there is you can't have this thing on a wire, for instance, of length L, because you put a charge there, those charge in the conductor will move around and redistribute. So this can't be a conductor. So like continuous charge, uniform, with another charge over here, not possible. Okay. With a conductor, can't be conductor like a wire or something. But regardless of this, just say this is just a fake problem, fake thing, something. You might say just mathematical models or whatever. Okay, so this is a very standard problem. Just we learned mathematical techniques that go in dealing with this kind of problem. All right, the law is, as far as the Coulomb law is concerned, Coulomb law is it's between two point charges. So the law is 2 point charges, but the problem is continuous charges. Which means I need to come up with, when we set up the problem, convert this into point charges. So we'll convert, looking at this, we divide this up into little pieces, maybe n equal pieces, and we'll look at one of those pieces and say how much will this apply force on that, and then we try to sum up contribution from all of these. So to set this up, you will need to some kind of coordinate system, and because this is symmetric, we can call this x-axis. The charge q is over here at distance d, so this guy's coordinate is d0, and some arbitrary element over here, it goes from L over 2 here and minus L over 2 here. You can apply symmetry to say that the force from this, whatever the force from this much is, will be equal in magnitude to the force of this much, right? The net force. So you could just do this and double what you get the answer for. Okay. So this guy's coordinate is 0 some y, and it exists between say y and y plus dy. So dy is that infinitesimal, and how much charge there will be, so the length of this thing is dy, so the length of this thing is dy, and it says the charge says lambda coulomb per meter. So that means the q in let's call it dq, that exists over here, call that charge dq. Dq will be lambda times dy. So now you already see the integration will take place along the y. This is the y-axis, this is the x-axis. Okay, so if this was the point charge, if this was my charge, you can see from the Coulomb's law is whatever, say this is q1, this is q2, and f on say q2 will be equal to k q1 q2 over the distance between them, r square, and then you have a u hat, and this is on q2, so q1 to q2 direction, right? This is the unit vector in that direction. So over here it's going to be it will be either unit vector this way or this way, one of these directions. So it says I want from this to that, so unit vector I want is in that direction. So unit vector is usually, you can say, just take positive to positive and then which way it will be pointed. Okay, so if this was a positive, this is positive, this will point that way, and that will be the direction of the unit vector. And if this was negative and this was positive, then the sign of these guys will actually take care of flipping this direction. Okay, so let's see. We have this, we can write down df from this guy. We just write down in this way just to indicate it is from the infinitesimal, and you have a k, and if you remember, k is 1 over 4 pi epsilon naught, and which has a value of 9 times 10 to the power 9 Newton meter square over Coulomb square. Okay, so k, then you have a let's call this d capital Q. Okay, and because we use the Q here, so don't want to get confused with the variable. So Q times, this is a different amount of charge. The distance between this and this, you can see if this is d and this is y, then this is square root d square plus y square. So squaring that gives me d square plus y square. And then we need a unit vector. So unit vector in that direction will be so you can see that it's going to be d I hat d minus 0. So this is, you can see the q1 to q2 vector. So take this, subtract that away, so minus 0 y j hat and square root of d square plus y square. This is the unit vector. Now dq, we can just say dq, let's write down dq is lambda dy. And to get the f, all I need to integrate is minus L over 2 to L over 2 to get the whole thing, right? You can see right here that this will distribute in two things. Let me write that down because I want to make this point. KQ lambda is constant. So it's going to be two integrals, minus L over 2, L over 2. I already see the answer, but I want to make sure that you, then this one d comes out because d is constant, and I have d square plus y square 3/2. Then I have minus L over 2, and this is I hat L over 2 dy over y times dy over d square plus y square 3/2. And this is d over here. Okay, so that okay, this is fine. Now notice right away that this limit is symmetric, but the integrand is actually odd function of y. What the odd function means? F of y is odd if f minus y is minus fy, and you have symmetric limit. That will mean this integral will be 0. So this will be 0. There will be no y components, and you can already see from the symmetry. So if this is this way, there is exactly over here this other thing which will be pointed that way, and they out to just cancel and give me only net. So for every dy here, there's another dy there that gives you x direction net, and so there is a pair like that, right? So this part is 0. So this is the only integral I need to do. And there are, you can do a lot of different ways to do this integral. So this will be kq lambda d, and because this is symmetric and this is even, this is j hat over here, this integrand is even, I can make this 2 times 0 to L over 2 and make it I hat over here. I hat doesn't depend on y, doesn't depend on I hat, so I hat is constant put in front, and I have a d square plus y square 3/2. So that's the integral I have to do. Okay, I can change variable, bring the d square out. I can look it up, and so there are various ways to do it. Okay, I will do this integral and then I'll give you the answer. Okay, so there is a really simple way to do this, because you might be able to check that ddx ddy of y over square root of 1 plus y square, this over this, is actually equal to 1 over 1 plus y square 3/2. So you can check that, and if you check that, you can see that I can pull the d out, so make it d square, make it d cube here, so this becomes 1, and there comes y over d square. So take one of the d's, make it y over d here, and so now this, consider that to be a new variable, y over d, and let's call that a z. Then that's a z square. It's almost like that now. This would be when y is L over 2, then z going to be 2d, like that. So using this, I can just say I had kq lambda d, and there's a 2 here, this just lambda d square. This is the total charge. No, not total charge. Let's call it d, little d here, little d. So this is just lambda, and this one becomes, you can see that if call z, if you call that a z, then I'm going to get this z over square root of 1 plus z square and 0 to L over 2d, and over here with 0 it becomes a 0, so this is L over 2d. So I have I hat 2k q lambda L over 2d divided by d square root of 1 plus L over 2D square. So you can see this part here is just the total charge in the rod. Let me erase this and explore a little bit the consequence of this. Okay, so look at we just look at a little bit more closely. So we have I hat, so the F on Q is all along this direction, which we'll call I hat. We have a 2K Q, and let's call this capital Q. So net charge here, let's call it capital Q. And this 2 cancels this 2, so just forget this 2. And you have a D square. Then you have 1 over a square root of 1 plus L over 2D square. So a couple of consequences you can see that first of all, it's not just this, okay, but it's actually that multiplied by that. It's not like total charge, just put it over here and then you're done. No, that's wrong. So one consequence is, what if I put the charge way out there, say D going to infinity? Then this entire charge can be placed right over there, because if you take a limit here, this will be I hat KQ Q over D square, as if the entire charge was just placed in the center. Okay. If I place D close to 0, then you can see if I place D close to 0, like right over here, then it should cancel, right? The force from all the charge there, it is repelling, bottom one is repelling the other way, it should cancel. So let's see, if I have I hat KQQ over D square times D go to 0 is going to it's going to flip over, right? Flip over, and this would be going to infinity compared to 1, and so I'll get a 2D over L. So if I get if I am close to 0, why is it not going to 0? Okay, what do you think is happening if I put D go to 0? Well, you're going to find this kind of problem with limits when the charge is, you expect 0, but it's not coming out 0, because you can see that let's look at the charges over here, and when I place this charge on that, all these charges, you might say cancel, they cancel. But what about that little charge right on this charge and this charge right on top of each other? Their distance is 0. So even this one is of a dy, but which is lambda dy, but that one is actually not 0, right? Dy can be as small as you like, but not 0. So you can often find when you're doing a continuous charge problem, you will find that when you take limits, you have to be very careful how to take limits. Okay, you can't place one charge on top of another charge and expect it to be zero. So so in Coulomb's law, it says K Q1 Q2 over R square, you had R not equal to 0. So we are allowed to do all of this. We are allowed to take this limit as long as this is not allowed limit. In this case, I can go to maybe a epsilon and say what happens. So instead of going all the way to 0, you want to have some small distance. So a small distance, you can see, so a small distance is squared, and then you not equal to 0. So if you get very close right on top of each other, then you all these distances become you can say all these distances become small. All the distances are becoming small, and so the force becomes very large, and right at very near to it, but not exactly 0, because we're not supposed to take limit 0. So at that point is actually going to blow up, and it blows up pretty much continuously. You can see, if I say okay, go to 0 limit, of course this limit doesn't exist. Okay, so with that I'm going to stop this with a little bit of review of what happened. So whenever you come across a continuous charges, and we're going to come across a lot of continuous charges, like a line of charges like this, or a ring of charges in a ring, or you're going to come up with a disk of charges in a disk, or maybe a cylinder, surface of a cylinder, charge on a surface cylinder, or you might have cylinder all the way across, or you can have a sphere, you can have a spherical shell, or you can have a sphere filled with. So these are all continuous charge systems that we study. They're a good system and a lot of nice math that goes with it, but all of them will follow the kind of things that we did in solving this problem when handling line of charges. Okay, so this was so we did dq. Our strategy was to break this up into small pieces, and from each piece, from a representative piece, you figure out what the formula would be, and then you gotta do the integral. Those of you who don't know how to do integrals, you're probably not going to encounter this kind of problems, or you'll be given the final answer to look at. Maybe you look at a large limit like that, but if you are required to use calculus in your physics class, you will be forced to have this kind of problems, and there's a lot of practice goes on in this problem. So you learn how to think in terms of infinitesimals. So this particular way of thinking is like taking a continuous problem and breaking up into a problem for an infinitesimal. That is going to be a very important skill for you, and the more problems you do, the more practice you do, you're going to be get better and better at that. Okay, so maybe you want to go over this problem again and practice a couple of times. Okay, take care, bye.